everyone to the session. I will present the joint work Fotakis and Orestis Papadigenopoulos about the scheduling problem. So this is the scheduling session. Now, pointer not working. Okay. What is going on? The ticker is just on, right? But this is
maybe you are working against each other right now.
So this is unrelated from my clicker's not working. Since I started Zoom, it was working before. I don't think it's a problem with the clicker, it's with my computer and Zoom.
Try sharing the screen rather than
okay, maybe that's
András. Can you mute yourself, András? Okay, thanks.
Okay, so now here we go. All right, so I will present a scheduling problem, which is called generalized malleable scheduling. And the little difference from standard scheduling problem is, so as always, we're given a set of machines M, a set of jobs J, but now we are not forced to run every job on a single machine, right? So usually we assign each job to a single machine like this here, and it takes some processing time. But now we have the option to process jobs in parallel. So, for example, we could decide to process this job in parallel on these two machines here, A and B. And the processing time of the job now is not given as a fixed number, but it's given by some function here, fj. So f sub j of s gives us the time it takes to process job j on a set of machines s. And we can assign each job to an arbitrary set of machines. And what's important now is that these jobs then will be processed in unison simultaneously, which means the machines, they start processing the job at some time and they will finish at the same time. So they will be busy for the same interval of time, and it's non-preemptive, and every machine can only process a single job at any given time. So what we have to do is we have to find a subset of the machines for each of the jobs, and we have to decide on the starting times for each of the jobs in such a way that no machine is busy with more than one job at a given time. For example, we could process this job on all three machines, and then maybe the other jobs we process like this. So you see that, now every job is processed in parallel in unison. And our goal is to minimize the makes time, so which is the time when the last job finishes. It's the model here so far. So that's a pretty generic model. I didn't say anything about functions yet. Let's assume they're given by some value oracle, right? So we can just give them some set S. We have an oracle that tells us how long it will take and gives us the FS. So you could ask, why is this generalized up here? So because malleable scheduling in general, so it's actually this model where you can distribute jobs. So the generalization here is that classically when people talk about malleable scheduling, what they actually talk about is the identical machine case. So this is the case where the processing time of a job just depends on the number of machines, right? Because all the machines are identical. So when you assign a set of jobs to machines, the processing time is just a function of this cardinality of the set. And the typical assumptions that are made in literature are that, okay, if you take more jobs, then the processing time will likely go down. But the total amount of work that it takes to process the job doesn't go down. Yeah? So this function here, f of k times k, this is non-decreasing. So f k times k, you can think of this as the number of machine hours it takes to process the job. Yeah? So number of machines times the time each of the machines take, that's the number of machine hours, the work. And what's behind this is that the assumption that there's no synergies. When you combine multiple machines, then together they will not be faster than the sum of their individual speeds. Yeah? So that's one interpretation of this. And for this problem, for the identical machine case, that's very well understood. So there have been constant factor approximations for quite some time, and a bit more recently, there's this polynomial time approximation scheme. Right? So this problem is actually solved in the sense that it can be solved as well as the classic case of non-malleable scheduling. So now you could ask, what about the case of non-identical machines? And there's also some work of this prior to what I'm presenting. I don't want to go too much into detail here. So there's a related model that's called splittable jobs. There's another generalization that actually we did previously, which is with job-dependent machine weights. I don't want to talk about the details, but the main message here is that in both of these cases, the power or the contribution that a machine has towards a job can be expressed by some scalar, right? So by some number that expresses how well this machine processes that job. And that inherently limits the model in the sense that we don't have any combinatorial effects between machines, right? So in general, there could be interaction effects where I combine some machine with another machine and together they won't work well, but with a third machine, the first machine maybe will work very well, right? So these type of combinatorics, they are missing in the models that are present so far. So that's what we want to capture. And of course, we will have to make some assumptions on the processing time functions. That's what I now want to tell you. What are the assumptions? So it turns out that rather than formulating the assumptions in terms of these processing time functions at J, we rather focus on what we call the processing speed, so which is 1 over the processing time. Right? So if you imagine your job is just 1 unit of work in some normalized sense, then 1 over f of 1 over the time is the processing speed of the set of machines. And now I call this G of J. So Gj now is the processing speed function that tells me how fast are the machines in S when processing the job J. And for this, now we will make some assumptions, and we want to capture this no synergies idea from the identical machine case. And now no synergies will translate to some sort of discrete concavity on these functions. Right? And there are many different ways to express such concavity. So for example, we could just assume that the functions are subadditive, which would mean that if we combine two sets of machines, S and T, then the processing speed of the union should not be more than the sum of the individual speeds, right? That's subadditivity. We could then also go to submodular, where we notice that here we actually double count what is in the intersection of S and T. So if we add this also to the left-hand side, we get submodularity. There's also a notion of fractional subadditivity, which is somewhere in between subadditivity and submodularity. So in fact, all the concepts that are listed here are actually specializations of one another. So here subadditivity is the most general one, and matroid ranks at the bottom, that's the most special one. And every function that is a matroid rank is M natural concave, that's then supermodular, and every function that's supermodular is fractionally subadditive, and every function is subadditive function is subadditive. Right, so these go from most general to most special down here. I will actually focus on M natural concave function, but I will not tell you what this is right now. It's also known as cross substitutes, but wait a little bit until you get the definition. I just want to mention, so the last case here, matroid ranks, what I mean by this is that you have so the function is just a rank function of some matroid, where the matroid depends on the job, times some factor here, so it doesn't get too boring, right? So that you almost scale the amount of work that has to be done for the job. Okay, so what we have for these different types of functions are the following results. So it turns out that for the most general cases, it's actually quite hard, and these are actually unconditional hardness results. So there's inapproximability, at least with this type of value oracle, you cannot do anything. That's not conditioned on D equals empty anything. But for the case of submodular functions, there's a logarithmic approximation, and actually it's open whether we can have a constant factor here. So that's one open problem. For matroid ranks, we get a 5 approximation, and then the result that I actually want to focus on is this constant factor approximation, where the constant is actually quite big. It's something like 190 for these M natural concave functions. Right? So that's what I want to focus on. And to give you an idea of this result, so we first have to look at the relaxation, and here's the relaxation of our problem. We want to get rid of a complicated part of the scheduling problem, which is the timing. The timing in the scheduling in this case is quite annoying. Let's get rid of it. So what we're looking for in the problem is a schedule, which consists of the assignment of the machines plus starting times. But now we could say, let's just look at at the assignment problem, so where we just assign a subset of machines to each job. So every machine gets a non-empty subset of jobs, every job gets a non-empty subset of machines. And then we look for every machine, we look at the total processing time of all the jobs in which this machine participates. Right? So we just sum this up, which would be the load of the machine. And then we look at the maximum of those and we say that's the make span of the assignment. So here we don't have starting times. We just look at the amount of work that every machine does. In non-malleable scheduling, so in the classic setting where every job goes on a single machine, if we have an assignment, we can just run the jobs on each machine in arbitrary order and we get a schedule. And that schedule will have the same make span as the assignment. So the problems are equivalent. In malleable scheduling, that's no longer the case. Right? You can see it here. So in this example, you have an assignment where if you assume that you have unit processing times here, every machine has a load of 2, but you cannot schedule them in such a way that you get a schedule which ends at time 2. Right? So assignment and scheduling are different in malleable scheduling. The question is how large can the gap be? Can be bounded? And the fortunate news is that under the assumption that I just presented, so when the processing speeds are submodular, in particular, then we can bound this by a constant factor. And to get there, we can show that we can transform any given assignment into an assignment with a nice structure, which we call well-structured assignments, which we then can schedule easily. And this property is as follows. So if you look at any given assignment, we can partition the jobs into 2 types, right? So jobs J1, they are the jobs that go on a single machine. And then jobs in J2, those are the ones that get multi-machine jobs. And the well-structured assignment is just one where every machine only participates in one of the multi-machine jobs. And then when you have this, it's very easy to get a schedule because you just start on each machine with its single unique multi-machine job, and then you process the remaining jobs in arbitrary order because those only go on that single machine. Right, so once we are there, we can have a schedule, no problem. And our first result is that if you have submodular speed functions, then you can turn any assignment with some make span C into a well-structured assignment, which then can be turned into a schedule with a constant blow-up in the make span. And that constant blow-up is, in this case, this factor of 3.16. I don't want to prove this because actually I gave a few talks about this result already this year, and you certainly can find some recording of this. And you can also ask me, of course, sometime this week if you're interested in this. So I will not prove it, but what I want to mention is that within the proof, one part of it shows actually the structural results so that you can find a well-structured assignment where each job, each machine gets a multi-assigned, multi-machine job that can be processed within 2 times this make span C, and then the single machine jobs can also be processed into C. So each of these 2 groups of jobs can be processed into C, and this already gives a nice idea for an approximation algorithm, actually a general approach towards approximating not only now this scheduling problem, so not only reducing an assignment to a well-structured assignment, but also starting from scratch and finding a good assignment that then can be turned into a schedule. And this idea is as follows. So let's assume somebody told us about these 2 sets, J1 and J2. Right? So let's assume we somehow found out about this. Then what we could do is we could schedule the jobs in J1 just using some classic scheduling algorithm, right? So for non-malleable scheduling, there's Papadigenopoulos gives us 2 approximation for this scheduling on unrelated machines. So we can handle those jobs. And the remaining jobs, now what we would actually like to do is we would like to find a partition because every machine should only get 1 job. So we would like to partition the machines into 1 set for each job in this set J2, such that the minimum speed that's received by any of the jobs is as large as possible, right? And that will then determine how long it will take to run these multi-machine jobs. So the problem is that this is still a hard problem. Maybe it's easier if we try to optimize the sum, right? So if we try to maximize the sum over all the speeds that we assign. this is called the welfare problem. So now we want to maximize social welfare among the jobs. The problem here is if we do that, then it could happen that one of the jobs gets a lot of speed, and another job goes empty, and then we have a very bad schedule. So what can we do against that? We could just truncate the jobs, the processing speed functions. So we're not interested in getting a job that is very, very fast, that finishes very, very fast. So to even it out, we truncate all the processing speed functions at 2 divided by c. Right? And if we do that, then now knowing from the previous result that there exists some assignment that runs all these jobs in time 2c, we know that this also has a solution where each job receives 2c. And if we can solve this problem exactly, then the sum here will be cardinality of this set J2 times 2c. And this is only possible if every job really receives 2c. So in that case, then maximizing the sum is the same as maximizing the minimum. Right? So we can solve this with the welfare problem if we can solve it exactly. So the good news is for matroid rank functions, that's possible. So if we have matroids, then this is just matroid union. So we can solve this exactly. We get a 5 approximation. The reason why we don't get a 4 is because we don't know about J1 and J2. And for submodular functions, unfortunately, we cannot solve this exactly, but there's a constant factor approximation for this. So we can, for example, use the greedy algorithm, and then you get a 2 approximation. And with this 2 approximation, now it could happen that some jobs go empty-handed, but you can now do this iteratively, because when you solve this welfare problem, you can at least be sure that at least a constant fraction of the jobs will get a constant fraction of 2c. And then you do this repeatedly, in every iteration, you just get rid of the constant fraction of the jobs, so you get logarithmic approximation. And so that's the general framework. And now, of course, there could be hope. So now for these unnatural concave functions to also approximate those, the problem is these are not closed under truncation, so this trick here doesn't work anymore. So these will be much more tricky, but now it's about time I tell you what are unnatural concave functions, right? And here's a definition. There are many equivalent definitions. So I take this one that's using the greedy algorithm to define it. So an M-natural concave function has the following property. Let's say I have prices for all of the machines. So each machine or each element now has a price of our ground set M. Each element has a price. And now I want to maximize the utility that I get from it. So I want to pick a set S that maximizes the utility that I get minus the sum of the prices. And M-natural concave functions are exactly those functions for which the greedy algorithm finds an optimal solution, whatever the price is, for any set of prices. And the greedy algorithm is just the greedy algorithm that you would think of, the one that starts with S being empty and then always adds the element that maximizes the increase in utility minus. If you're interested in more about this, so here's some nice surveys and of course the book by Rota. And I would also assume that Lazzi will also talk about this probably in his talk on Friday. I saw these are closely related. So you could ask, how does this fit into scheduling? And here's an example of an M-natural concave function that actually is motivated by scheduling. And I learned from looking through the abstracts of the talks and seeing Lazzi's talk that these are actually called Prado valuations. So the setting is the following. Assume that every job has a set of slots, Vj. So you have here a set of slots, Vj, and each of these slots represents a role that a machine could potentially take when contributing to that job. And we have a graph that so it's a bipartite graph here, the machines, here are the slots, and the edges have a weight, so each edge is a weight that tells us what would be the contribution to the processing speed if we assign that machine to that slot for that job. And in addition to these slots, we have a matroid on the slots that gives us some constraints. So in this example here, I have a partition matroid which says these two slots here, only one of them can be used at the same time. Of these two here, only 2 of those can be used. We cannot use all 3 of them, and here this one doesn't have the constraint. Yeah, but in general, you have some matroid here, a matroid constraint. And now what we're looking for is a maximum weight matching. So if you want to evaluate Gj of S, then we restrict this side of the bipartite graph just to S. We ignore the machines outside of S, and now we want to find a matching, a maximum weight matching from these machines in S to the slots that respects these matroid constraints. So we can only use a subset of slots that is in the matroid, and we want to maximize the total weight that we get. Yeah? And this maximization problem then gives us the speed that these machines can contribute to. Right? And this type of function is an unnatural concave function. And the special case of this are also weighted matroid ranks. So now to get a constant factor approximation for the problem, the trick is actually to extract a weighted matroid rank function from the general natural concave function. Yeah, so we are not given, this is just a special case, we are not given any of this, and in general, natural concave functions can also be different. But what we can actually show is that using some LP, you can extract a weighted matroid rank. So what I mean by this is the following. So we have some linear programming formulation where we have a variable x as j for every subset of machines in every job j. Yeah, so that it's a very natural LP that you would also come up with if you think about the problem, probably where every job has to be processed. So the sum of these x as j has to be 1 for every job. And there's a coefficient here. This coefficient smoothes the it essentially prevents us from using assignments that would be too slow. Yeah, we get some make span C, and there might be some assignments that are too slow, and you can smoothly cancel these out, and that's this alpha here. And then you have a make span constraint for every machine, right? You just sum up the total processing time of all the jobs in which a machine participates, and this should be bounded by C. So this is this configuration LP. And now what you can do is the following. So using LP duality, complementary slackness, and the unnatural concavity of these functions dj, you can extract from a solution to this LP. So you compute a solution to this LP, and you extract a weighted matroid rank by this from this. So what we get is we get a matroid and weights, and the weights here lambda. So they're expressed by mu I divided by lambda j. These are the dual variables for these make span constraints for the machines and for the job constraints here. So these are the weights, and you get a matroid for every job, which comes from the fact that every element in the support of a solution so an optimal solution, you could maximize, for example, the amount of free time on every machine. So an optimal solution here, every set in the support will be a maximizer of some natural concave function, and these maximizers, they generate a matroid. So that's a known result. So you can expect a matroid here, and then you can express approximately with the loss of a constant factor. You can express this dj of S as the maximum over the matroid, where you restrict the matroid to the set S, and then you look for a set that maximizes within the matroid the rank. So the weighted rank, or the total weight. Okay, so that's the first simplification. So now instead of having these arbitrary and natural concave functions, we have a weighted matroid rank. And then we can get rid of some more jobs. So we can get rid of jobs that are primarily scheduled on fast machines. Those we can just schedule on a single machine with using, for example, Lenz-Moistadov, the algorithm of Lenz-Moistadov. We can also get rid of no, my pointer is not working anymore. We can also get rid of some jobs that are assigned to slow assignments, so to sets where the total weight is relatively low. And then what remains is a case that's much more simple. It's not yet trivial to solve this, but in this simple case, importantly, now every machine will only participate in a constant number of assignments. So not in terms of the number in the support, but if you sum up the XS variables, then these will be bounded by a constant by 26, it happens to be. And still every job will receive enough weight. Yeah, so now we approximate our speeds by these weights, and if every job receives enough, then that's fine, and you can model this as a polymatroid intersection problem. Yeah, so this can be modeled as a polymatroid intersection problem, and then you take this solution to the LP, you plug it into the polymatroid intersection LP, you get a fractional solution, and now because of total dual integrality, you can also get an integral solution. The problem is this constraint here, you cannot add this to the polymatroid intersection. You cannot just add this. This would destroy all the structure. So you have to deal with this with some additional rounding. You have to round the weights to powers of 2, and then you look into groups of machines with these powers of 2 weights, and then you say for each of these groups where it's this power of 2 for the machines, I have to have a certain demand. I have a certain integral demand. I have to have so many machines of this type, and this you can actually add as a constraint in the polymatroid intersection, and then you can get an integral sum. So that's the overall plan for this. Yeah, I think I will stop here with gently going over into the open problem session by mentioning once again. So the open problem here is this is for M-natural concave functions, but for submodular speed functions, we don't know whether there's a constant vector approximation. I can totally imagine it's true, but there are many parts here where we use M-natural concavity, so there will be a lot of work to be done here. Okay, thank you.
Thank you very much.